deliver the workloads and applications that businesses rely on. Containers have broad appeal for the ability they provide to easily package an application and all its dependencies into a single image that can be promoted from development to test to production without change. That seriously simplifies the testing and debug process. Containers also make it easy to ensure consistency across environments, including physical servers, VMs, private or public cloud. You're not worrying about all of those deployment configs in those different environments when you're deploying containerized applications. All of this helps teams to more easily develop and manage the applications that drive business value. Rarely, however, are enterprise applications delivered in a single container. Also, enterprises have additional requirements for application deployment. They need resiliency, high availability, failover, the ability to scale up and down as demand increases and goes away. In other words, a container orchestration platform is needed to effectively manage containerized applications. Kubernetes is the most popular container orchestration platform. It's a distributed application platform that maintains declarative state for the applications deployed on the platform. Kubernetes includes a control plane, the master nodes, and the data plane, also known as worker nodes, where the applications run. The control plane monitors and maintains state across the cluster, both for the platform and for application components. Kubernetes has won the container orchestration wars. More and more Kubernetes clusters are being deployed, and more business-critical applications are running on those clusters. OpenShift is Kubernetes for the enterprise. OpenShift makes it easier to move your application stack from monolith to multi-tier to microservices. It makes it easier to increase utilization of existing infrastructure, and OpenShift has features built in that help organizations modernize their process. OpenShift is present across multiple industries. Let's take a quick look at some of the OpenShift customers in the banking and financial services space. So Macquarie is able to take advantage of OpenShift for faster time to market. Deutsche Bank has been able to improve server utilization with their use of OpenShift. And Emirates is really focused on OpenShift for the use of innovative technology that it provides. If we take a little bit of a deeper look at what Macquarie gets from using OpenShift, here's how they frame it. They describe the challenges that led them to adopt containers and Kubernetes this way. Digital is requiring us to rethink everything we do about how we interact with our customers. We have to redefine the customer experience to make their lives easier. We have to re-platform to be able to reshape our business. And bottom line, they need better response time for their customers. With OpenShift, Macquarie has been able to move their microservices and applications onto OpenShift in a few seconds. That's a huge impact to their business. They release daily, within minutes, with zero downtime. They deliver faster without losing control or visibility of the systems. And this new model helps them hire and retain top talent. AI and ML is another area where OpenShift shines. And again, here we have two different customers talking about how they've been able to use OpenShift for their AI and machine learning use cases. So BMW's challenge for their connected drive system is that they need to deal with 1 billion connected drive requests per week. And they also need to be able to deploy services in new markets on a regular basis. BMW Group uses the public cloud to gather data to create new and tailored customer experiences. They chose Red Hat OpenShift Dedicated because it gives them the scalability and resilience they need for future growth. HCA Healthcare is focused on how analysis of large data sets can help them improve healthcare around the world. Their leadership identified sepsis rates as a key challenge that data could help solve. Sepsis is a condition where the body's immune system has an overwhelming response to infection. Sepsis is responsible for 270,000 deaths per year in the U.S. alone. So HCA group sought to use predictive data analysis to establish a standardized digital approach to sepsis detection. They deployed this solution on OpenShift in order to support their care providers with modern tools and a machine learning platform and cloud computing for flexible, scalable, and fast results. All of these organizations have different security and regulatory requirements that they need to meet. So how does OpenShift help them ensure that security requirements are met when they're deploying and using new technologies like containers and Kubernetes? Traditional security checklists with many manual processes are simply not adequate for this new world. They don't scale when applications come and go in an automated fashion without human intervention. And in fact, the servers themselves can come and go without human intervention. To maintain security and benefit from the speed, agility, and resilience that Kubernetes enables, security solutions must be both proactive and reactive. Security must be considered at every stage of your application and infrastructure lifecycle. And you need to think about process and people here too, right? To really be effective, you need to shift security left. You need to integrate security experts in with your application deployment and infrastructure teams so that they can work together to find the best way to meet the security requirements. Defense in depth is created by considering security again throughout the stack and the life cycle. Design for security requirements early on, both for your applications and your infrastructure. Collaboratively develop and communicate security policies and procedures. Build security capabilities into your application and your infrastructure, again, for that proactive security. Run on trusted platforms that have built-in security features. And manage with automation to maintain an up-to-date environment to consistently monitor assets and access and usage. And then based on that monitoring and analysis of the data you collect through your management, adapt as needed as conditions change on the ground. So again, security must be a continuous ongoing activity with automated checkpoints throughout the life cycle for fast and effective feedback to your operations and development teams. In a true DevOps world, all stages need to inform the other in a continuous loop. Here are some of the specific security capabilities and solutions that our webinar series will discuss. In today's session, we're going to focus on some of the key security capabilities that are built into OpenShift, with a particular emphasis on those that enable a multi-tenant cluster. Linux is the starting point when it comes to container security. At bottom line, Linux containers are Linux processes running on a Linux host. So you find that securing enterprise use of containers requires an operating system that can manage multi-tenancy of the container runtime. You need an operating system that can secure containers at the boundaries, securing the host kernel from container escapes, and securing containers from each other. There are multiple levels of security and a lot of history involved in securing containers on Linux. Linux namespaces, SE-Linux or Security Enhanced Linux, C groups, and secure computing mode are 4 of the security features available for securing containers on Red Hat Enterprise Linux. We're not going to be able to dig into each of these, but we'll touch on a couple of them for key points. Linux namespaces provide the fundamentals for container isolation. A namespace provides abstraction and makes it appear to the processes within the namespace that they have their own instance of global resources. SE Linux is used to keep containers isolated from each other and from the host. SE Linux allows administrators to enforce mandatory access controls for every user, application, process, and file. SE Linux has been shown to mitigate more than one container runtime vulnerability over the years. It's the brick wall that's going to stop you if you manage to break out of the namespace abstraction. C groups, or control groups, limit and account for and isolate the resource usage, that is CPU, memory, disk I/O, network, of a collection of processes. C groups are used to ensure your container won't be stomped on by another container running on the same host. And finally, a secure computing mode profile can be associated with a container to restrict available system calls. You can further enhance security for your applications and infrastructure by deploying your container platform and your containers to a container-optimized OS such as Red Hat Enterprise Linux Core OS. Core OS is an immutable operating system. It is booted from container images, and it contains only what is necessary to run OpenShift. This reduces the attack surface and minimizes the ability to make any changes on the host itself. RHEL Core OS is managed by OpenShift. It is the required operating system for the OpenShift 4 control plane, which provides significant advantages. This actually makes it much easier to keep your host OS up to date with the latest fixes. We'll talk about that a little bit more as we continue. So we also need to think about how to design your application container pipeline. Right? As with any application, managing production builds is a key part of securing the software stack. Remember that with containers, you never patch a running container. You always rebuild and redeploy, which means that your CI/CD pipeline is strategic, right? You need to plan ways to build security capabilities into that pipeline and to automate as much of that process as possible. And you're going to want to think about the various tools that make that easier. You can see some of them called out here. You can see that there's a mention of some code quality scanning tools, vulnerability scanning tools, and unit test is also a key element. So while our conversation today is focused on security, unit tests have a key role to play, and automated testing in general, in giving you the ability to quickly rebuild and redeploy your containers, right? You want to be sure that your rebuilt item not only passes its security tests, but also your functional tests. So this is something you really need to make sure that you plan for as well. OpenShift provides certified Jenkins container images, as well as a number of Jenkins plugins, to make it easy for you to integrate Jenkins with OpenShift and to build your own CI/CD pipelines in OpenShift. Teams can customize OpenShift CI/CD Jenkins workflows in OpenShift, but you also have choice about more than that, right? You can run Jenkins as a service on OpenShift with your Jenkins masters and slaves in OpenShift itself. You could use Jenkins in a hybrid mode where perhaps you already have a Jenkins master that runs outside a cluster. You leave it where it is, and you run your Jenkins slaves in OpenShift to build for extra build capacity when you need it. Or you can use whatever existing CI/CD you have in place today and simply deploy your container images to OpenShift without needing to make a change. One of the things that we're working on in OpenShift as technology continues to evolve, our next generation CI/CD pipeline will be built with Tecton. We'll continue to support Jenkins as a pipeline in OpenShift, but we see a lot of value add coming from Tecton for microservices-based apps and the newer generation applications. Wherever you manage your CI/CD pipeline, you also need to think about the sources for the external packages that you pull in as you build your applications. So Today's applications typically include open source components such as Linux operating system dependencies that you need to add for your containerized apps. You may also want to be using an Apache web server. You may be using JBoss EAP, a Postgres database, Node.js, Python. Containerized versions of these packages are readily available so that you don't have to build your own. But where they come from matters. Red Hat provides a large number of certified images, including RHEL-based images with those OS dependencies that you need, as well as various language runtimes, middleware, databases, and more, all available in the Red Hat Container Catalog. Red Hat certified containers run anywhere RHEL runs, from bare metal to VMs to cloud. Certified containers are supported by Red Hat and our partners. Container image content is packaged from known source and is signed so that you can verify on download that you got it from Red Hat. Furthermore, Red Hat also provides security monitoring. Our catalog includes the Container Health Index. We expose the grade of each container image. Containers are graded based in part on the age and impact of unapplied security errata to all components of a container, providing an aggregate rating of just how safe a container is that can be easily understood by security experts and not experts alike. When Red Hat releases security updates, such as fixes to glibc, drown, dirty cow, run C vulnerabilities, we also rebuild our container images and push them to the public registry. Red Hat security advisories alert you to any newly discovered issues in our certified container images and direct you to the updated image so that you can, in turn, update any applications that use that image. You should also be sure to store both external images and any custom container images you build in a private registry. So while you can just pull down external content from public registry, there have been cases when those registries have been unavailable for a period of time, plus content changes on those registries. So if you're relying on external content, you really want to save it locally to be sure that you've got exactly what you intended to use. You can use the OpenShift internal registry or a registry that is external to OpenShift. Knowing that new vulnerabilities are identified daily, you want to proactively check the contents of those container images over time. So in addition to integrating automated security tooling into your build and CI process, you should run vulnerability scans on the images stored in your private registry. You want to look for scanners that will notify you when new vulnerabilities are discovered on previously scanned content. Red Hat Quay with Claire is one offering, and you'll be hearing from our Red Hat partners about their offerings around vulnerability scanning as well. So now we're going to step back and take a look again at the platform itself. You also need to be sure that the platform, the container platform, is appropriately secured. Again, the control plane determines which containers should be deployed to which hosts. It manages shared resources like networking and storage. It enables containers to discover each other, and it prevents containers from discovering each other. And it provides the features that allow you to automatically scale capacity to meet demand. For these reasons, the Kubernetes masters are a central point of access and should receive the highest level of scrutiny. Multitenancy is a common usage pattern for OpenShift customers. In a single enterprise, they may have multiple teams from multiple different business units using the same cluster. And there are many features in OpenShift that support that. So one of these is the way OpenShift takes advantage of the built-in security capabilities in Red Hat Enterprise Linux. We do that with something called the security context constraint. This is a feature that is available to the OpenShift admin that gives them an easy way to manage all those knobs that are available in the Linux OS for controlling container isolation. Security context constraints have been available in OpenShift since OpenShift 3.0, Red Hat contributed that code upstream to Kubernetes, and the upstream version of that code is called pod security policies, although that is still beta. So for the time being, OpenShift continues to use security context constraints. Security context constraints set the conditions that a pod must run with in order to be accepted into the system and provides defaults for certain fields. So 7 security context constraints are available out by default in an OpenShift cluster. You can also create custom SCCs if you wish. The restricted SCC, which is the screenshot that you see here, is the one that is provided to worker nodes by default in OpenShift. This means that by default in OpenShift, no containers can run with privilege on the worker nodes. Furthermore, SE Linux is always on the host that OpenShift runs on, and because OpenShift understands how to work with SE Linux, the containerized applications that you deploy to OpenShift don't need to understand it. Although, if you're really strong with SE Linux, one of the things you can do with security context constraints is add additional SE Linux context in this feature. For the particular pods you're deploying. But you'll also notice that in addition to not being able to run with privileged, there is no access to host network or host ports. All of this enabled by default. Security context constraints ensure clear isolation between container and the underlying host and limit the ability of the container to negatively impact the infrastructure or other containers. As we continue up the stack, we want to take a look at Kubernetes namespaces. So we've been talking about Linux namespaces and the isolation they provide. Kubernetes also has a concept of namespaces. In OpenShift, we add a little metadata to Kubernetes namespaces, and we call these projects. So that's the way in which at the Kubernetes layer, you can isolate running applications or services across teams, groups, and departments. So this graphic shows 4 different namespaces or projects in OpenShift terms, and you can see that this user is only able to access the payment dev project. That user is not allowed to access the catalog, the inventory, or the payment project. There are additional layers of control provided through identity management and role-based access control. So that's kind of tightly coupled with this concept of projects, right? Both users and services are provided role-based access controls. Users are managed with outside identity providers. OpenShift includes a built-in OAuth server that helps identify the person requesting a token and determines a mapping from that identity to the OpenShift user. However, the actual username and login is always managed through an external identity provider that you configure to work with OpenShift, and this is just a subset of those that are available. In addition, of course, you need role-based authorization, right? Access is only a piece of it. So OpenShift RBAC, again, can be used for both project scope or cluster scope roles. So a user may only be given access to 1 or more projects. They may be given access to no projects at all. A cluster admin, of course, would have a cluster scope role. And RBAC is used to ensure that users are only able to take the actions that they have been given the permissions to take. So multi-tenancy at the host level, multi-tenancy at the Kubernetes platform level with project namespaces, identity access management, and role-based access control, and finally, multi-tenancy at the network layer with Kubernetes network policies. So applications or services running on a Kubernetes cluster frequently need to communicate with each other. For that reason, Kubernetes clusters require a software-defined network that manages all of the communication internal to the cluster. In OpenShift, any communication between the worker nodes and the master nodes is TLS encrypted by default. But all worker nodes need to be able to communicate back to the master nodes for health checks and management, et cetera. Network policies are about how you manage communication between the containers or pods running in individual projects on the individual worker nodes. So network policies give you fine-grained control. They allow you to specify how different groups of pods can communicate with each other and other network endpoints. So in this example, you see that a particular pod, you can use network policies to say that a particular pod in project B is allowed to communicate with another pod in project A on port 8090 and in a particular direction, right? But it's not allowed to communicate on port 5432. Similarly, you can see that 3 pods in project A are allowed to communicate with each other, but only one of those pods is allowed to communicate with another pod in project B. In addition to managing network policies for fine-grained control of your east-west traffic within your cluster, OpenShift includes cluster ingress and egress controls that are equally important to managing your network traffic and multi-tenancy. OpenShift 4 includes a new feature called Multis. Multis is a CNI meta plugin. CNI stands for Container Network Interface. This is how all SDNs talk with Kubernetes. As a meta plugin with Multis, you can configure more than one network interface per pod. One of the cool things from a security angle that you can do with this feature is that you can now separate the control plane and the data plane. You could use one of your network connections to communicate solely with the master nodes. So in this case, you might see the OpenShift SDN on East0 is the path that might be configured for communication with master nodes, whereas Net0 would be the path that would be used for any east-west traffic, service-to-service traffic between worker nodes. There are other use cases for Multis, but from a security angle, this is one of the cool things you get to do with it. Secrets management is also key. Kubernetes and therefore OpenShift comes with a key value store known as etcd. This is where all of the state information about the cluster is stored, all of the declarative data that OpenShift uses to ensure that applications are deployed as expected, that the cluster is behaving as expected. Platform secrets are stored in etcd. You can choose to also store application secrets in etcd, although you may also prefer to store them in an external vault. One of the key things here, though, is never store secrets in a pod definition or a container image. That's just asking for trouble. Instead, you want to be sure that secrets are made available as environment variables, volume mounts, or again, through external vaults. And you want to take advantage of the capability to encrypt the etcd data store to protect the data that is there. Newly available, also, OpenShift Service Mesh helps developers and project managers to add an additional layer of control to the east-west traffic in the cluster. So we talked about the capabilities that are available to you through network policies, and you'll perhaps recall that I mentioned that traffic between worker nodes and master nodes is encrypted. However, pod-to-pod traffic between individual projects or between pods in the same project is not encrypted by default in Kubernetes or in OpenShift. Service Mesh adds transparent encryption of that east-west traffic through the deployment of a sidecar. The app developer does not need to make the effort to actually build in that encryption. Service Mesh will take care of that for you. And also Service Mesh provides observability of distributed tracing of the traffic within the projects that Service Mesh is deployed in. So again, additional protection through encryption, additional visibility and traceability of the east-west traffic within your cluster. Of course, we need to think about storage as well. Not every application that is deployed is stateless. Many of them do require access to storage. So securing that attached storage is also important. OpenShift provides plugins for multiple flavors of storage: NFS, AWS EDS, GCE, persistent disks, Gluster, Ceph, iSCSI. A persistent volume can be mounted on a host in any way supported by the resource provider, such as read-write once, read-only many, read-write many. For block storage, OpenShift uses SE Linux capabilities to secure the root of the mounted volume, making the mounted volume owned by and only visible to the container it's associated with. And access to shared storage can be managed by adding the group ID of the persisted volume to supplemental groups of the pod. Finally, apologies, let's talk about reactive security features. So far we've really been talking about proactive capabilities that you can put in place. Now we're back to thinking about reactive capabilities. So you want to be sure that you have monitoring and logging in place on your cluster. Cluster monitoring is installed by default on OpenShift 4. This is done with the components that make up monitoring are Prometheus and Grafana. There are built-in alerts available. And also OpenShift offers a logging stack made up of Elasticsearch, Fluentd, and Kibana. Both cluster logs and application logs are collected and aggregated. Users can only see the logs for their projects, of course, or you can use your own logging stack. However, whichever logging stack you use, best practice is to make sure that you forward your logs to the security incident and event monitoring solution or SIEM of your choice for additional analysis and alerting. So again, your cluster monitor will do alerting on cluster events. SIEMs are really good at that next level of analysis to kind of look for any potential concerns that might not be caught by your cluster monitoring. Definitely an important best practice. Again, you want to keep your cluster up to date, so you want to be able to react to any newly discovered vulnerabilities. OpenShift makes that easy by providing over-the-air updates. It's a very similar experience to how you would update your mobile phone. The admin is able to select the version they want to update to. And again, both OpenShift and the underlying host OS, RHEL Core OS, are updated through the same mechanism with no application update. You can choose to auto-update if you wish. The way in which we prevent application downtime, again, because the host OS is being monitored through and managed through the cluster, OpenShift is able to, if a host OS update is needed for RHEL Core OS, OpenShift will go and drain a RHEL Core OS node, make sure that those workloads are moved to other hosts. It will apply the update to that RHEL Core OS node and then put that node back in service and continue doing that throughout all the RHEL Core OS nodes in the cluster. Again, host-level OS updates with no application downtime. We also need to remember that the applications themselves need to be managed and updated. There may be newly discovered vulnerabilities found in the code used to build the applications that you've deployed to the cluster. So we talked about the fact that some of the content in your custom images come from external images. One of the additional features in OpenShift that helps you monitor the status of the external images you're using is called image streams. Image streams track changes to any external images that you have chosen to store in your private internal registry in OpenShift. Image stream also integrates with automated lifecycle hooks that allow you to drive continuous integration and updates, so you could pull down that newer version of the external image that you rely on. You could kick off in an automated fashion a rebuild of whatever custom image uses that external image. You can put it through all your automated tests and automatically redeploy again if you choose to. You may, of course, want to have some manual steps built in. This sort of depends on the level of automation that you have built into your environment. But with the right tools in place and the right process, you can automate the entire process of rebuilding the application to incorporate the latest fixes, not just from those external images, but from any of your other code as well. Because containers start with Linux, OpenShift inherits RHEL's industry-leading container security practices and reputation. OpenShift builds on those capabilities to deliver a Kubernetes distro that supports enterprise multi-tenancy and facilitates regulatory compliance. If you get a chance, you can link to the 10 layers of container security to read kind of a little bit more about all of these. And being secure across the entire life cycle requires customers to be protected from all attack vectors, or as many as possible. Red Hat's security partner ecosystem enhances and extends the security of Red Hat OpenShift. We have partners in many areas, including identity and access management, privileged access management, CI/CD, container content scanners and vulnerability management tools, external certificate authorities, external vaults, web application firewalls, security information and event monitoring. In the next webinars in our series, you'll meet 4 of our top partners and learn about their view of the market, the problems they solve, and see how their products work. Here's a small glimpse of what's coming up in those next webinars. Aqua Security helps customers create applications that are secure by design, enabling agile DevOps and hybrid cloud deployment with no compromise on security or compliance. CyberArk is recognized as the leader in privileged access security. Ranked #1 by Gartner and other analyst firms, CyberArk is trusted by over half the Fortune 500. CyberArk's out-of-the-box integrations with OpenShift and Ansible provide powerful, centralized secrets management with all the enterprise-class security features. As Gartner's 2019 leader in the Magic Quadrant for application security, Synopsys solutions are built on a foundation of industry-leading technologies that ensure you get the most complete and accurate view of open source risks in your software.